But he announced a student, then he announced my student, then I'm going to announce another former student of mine, which is Ailín Ruiz de Zárate, is also in Paraná. So in this all in the family session, right, Ailín will be speaking in high order internal wave model. Ailín.
Thank you. In fact, first of all, I would like to thank the organizers for the opportunity. It is always a pleasure to be here at the IMPA. I studied here under the supervision of André Nagli, and then I moved to Curitiba to work at the mathematical department. We have this brand new building, and we are in the 3rd floor with air conditioning. I would like to talk about internal waves models that appear, internal waves that appear in the shelf, like these ones in the South Brazil shelf. This was taken by an astronaut, and you can find it in the Atlas of Oceanic Internal Solitary Waves. It was taken in 2002. The differences in temperature and salinity promote stratification in a way that layers are visible, are possible to identify. In between those layers, and the interface in between those layers, an internal wave evolved. That's what I want to study. In a very simplified situation in which I will consider only 2 layers, a rigid lid at the top, which is a great simplification because, of course, in the top there are surface waves. This is the perturbation of the interface, that's the internal wave, a flat bottom to begin with, and the 2 fluids with different physical properties that are considered to be immiscible, incompressible, and irrotational. So nothing is left from the fluids after all those simplifications, but still it is a reasonable model for this oceanic context. In the atmospheric context, it is more demanding. The atmospheric context is a little bit more difficult to study. So I will assume the coordinate system is positioned at the unperturbed interface. I will consider a shallow water regime for the upper layer. It means the depth of the upper layer is much smaller than the characteristic wavelength of the perturbed interface. The perturbed interface is denoted by eta, the function I want to find. On the other hand, in the lower layer, I assume that the depth is of the same, is comparable with the characteristic wavelength that configures an intermediate regime, the so-called intermediate regime, to distinguish from the deep water regime in which the second layer is infinite, which leads to the very well-known Benjamin-Ono equation. So this is a different situation, the so-called intermediate regime for the lower layer. For stable stratification, of course, the lower layer have the greater density. What else I need to talk? I think that's it. Those are our assumptions. And we start with the Euler equations for each layer. And continuity at the interface, no pressure jumps allowed, rigid condition lid at the top, impermeable flat bottom too. In principle, there is nothing to impose. When you choose the proper function spaces, you determine some decay, of course. I will talk about that later. I will follow. My presentation is basically about a seminal paper from Choi and Kamasa for the Journal of Fluid Mechanics in 1999. And I will reproduce what they did in order to explain better what we did later. So Non-dimensionalization is performed in the upper layer, introducing the so-called dispersion parameter, beta, which is a ratio, the square ratio of the upper layer depth and the characteristic wavelength. We assume that it is a small parameter, so we can perform asymptotic expansions. And here it is in the scaling, already helping with the second equation for the balance of momentum. The reduction we perform for trying to get a type of Businessky system. That's the target. So we make an average of the horizontal component of the velocity, and that will be u. Eta is the perturbation of the interface, and this is a system, an exact system of equation already known by Wu and also in Kamasa-Livermore paper of 1997. This is an exact system, but it is not closed. In order to close the system in our two functions, eta and u, we need to perform some approximations by asymptotic analysis. This equation is exact, and we will keep it that way. And with some asymptotic expansions and connecting the upper layer with the lower one by the continuity of pressure, we will be able to obtain a type of Businessky system. So we did we followed Cho and Kamasa. We did another non-dimensionalization, different from the previous one, but consistent in the variables that the both layers share. And we introduce a potential velocity, because the scale of the velocity components here is the same. It is not a shallow water regime. Bernoulli law, which is always so handy, and trying to express the pressure with information of the lower layer, a Neumann problem with the Laplacian because of the potential velocity appears, and solving this approximate problem, linear problem, we face with the so-called Hilbert transform on the strip that was already mentioned today. That is an operator that changes in the context of a Neumann problem, the Neumann information, the normal data into the tangential derivative. That's what the Hilbert transform in any geometry does. In particular, in this strip, we have this symbol for that linear operator. So in the wave number space, in the spatial frequency domain, we multiply by this hyperbolic cotangent. It is connected with the Dirichlet to Neumann operator, since its inverse compound with a spatial derivative is the Dirichlet to Neumann operator, in the proper spaces, of course. In fact, what appeared in our Businessky-like system is the composition of that Hilbert transform on the strip with one spatial derivative. That is a better operator to deal with. So Shoei and Kamasa deduced this strongly nonlinear reduced model. It is called a strongly nonlinear because non-assumption on the amplitude of the wave is made. So this should support large amplitude internal waves, in which we have this nonlinear equation, another one with terms similar to the Berger's equation. This is just a travel term. We can eliminate that if the references is changed. And here the dispersive term, dispersive, because it brings dispersion to the model in the same way Businessky model brings dispersion, but instead of a third order derivative, we have the composition with the Hilbert transform. So that's the basic idea that guides us. If we want a weakly nonlinear regime, then we introduce a small parameter for the amplitude of the internal wave. So we assume that this proportion here is small for A, the small typical amplitude. We call that the non-linearity parameter. In fact, it appears in front of the non-linear parameters, as you can see here. And this one is a model it is obtained assuming that the relation between the dispersion parameter and alpha is of this type. Of course, from a strongly nonlinear model, many options for a weakly nonlinear regime can be obtained. From this weakly nonlinear model, in the unidirectional wave regime, we can find an intermediate long wave equation. We prefer to work with the regularized version of the intermediate long wave equation. This is the equation I'm talking about that supports solitary waves. We can take those solitary waves and plug them into the two-directional system, and we observe they behave quite well. And solitary waves are very important because they served as benchmarks for the numerical model, for the theoretical model also. Here we have the opposite of eta, because eta is more like what I drew before, like a dark solid. And you see, the domain here is periodic. For computation, numerical computations, the domain is periodic. And when the wave returns to its original position, the agreement is quite good. Sorry. Or we can play with it and make it split in what is called the fission of the solitary wave. This is a traveling wave for this system, as you can see. And when it, again, returns to its original position, the agreement also is quite well. I will not talk about the numerical method, but it is the method of lines with spectral computations in Fourier space. Now, it is possible to improve that model, recalling this is the model when the pressure isn't approximated yet. It is possible to improve that model and to obtain a higher order model still for flat bottom by improving the approximation of the pressure beyond the hydrostatic contribution that we considered before. And the result is a system similar to the Grignani equations for surface waves, a system that was independently obtained by Suat, Garner, and Green and Nagy, but it is known as Grignani equations. So we did so, and after some computations, we have a strongly nonlinear model of higher order, which is very hard to treat so many terms, nonlinear terms involving the non-local operator. I found it very challenging, both theoretically and numerically. But we can make some weakly nonlinear versions that are more easy to treat. In particular, currently, I am interested in this model when we assume that the nonlinear parameter is of the same order of the dispersion parameter. A system very similar to the classical Businevsky system appears. It has a non-local operator. This one is missing in the Businevsky system for surface waves, but it is important because, well, this is what I'm doing now. Sorry, I have to mention. Janaína, my former PhD student, William, also from UFPR, is finishing his master dissertation, Daniel, from Federal University of Rio de Janeiro, also Cesar, are always helping us. Another colleague from the Federal University of Paraná, Igir. So we are trying to understand this model. Here, I think I only repeat the model. We are following an article from Maria Elena Schombeck. That one is a theoretical article. So we use subleft spaces of L2 type, and these are just some properties of the operator we are playing with, we use all the time. For example, to prove, to begin with, that the linear system is globally well posed in the proper subleft spaces, and the solutions stay in that space. I don't want to give more details. Since it is linear, we have the solution expressed in Fourier space by this matrix multiplication, in which the dispersion is important. This is the phase velocity. This quantity here accounts for the different phase velocities for each wave number. And comparing the phase velocities with the linearized Euler equation phase velocity, we see that the higher order model not only captures the component that correspond to the lower layer, this one here, but also improves the approximation of the term that correspond to the upper layer. So comparing these two, the phase velocities are more accurate in this higher order model, and that's very important to guarantee that the wave travel at the correct speed, even in the nonlinear case. Just to show both in the small wave number, large wave numbers, this one, there are two that are very similar, Euler and the higher order model, and the lower order model, the original from Choi and Kamasa here. Also in the dispersion relations, we can compare the order of approximation, and the higher order, of course, is to be better. For this higher order nonlinear model, weakly nonlinear model, again, we have our operator, non-local operator, just to show its phase in the physical domain. It is a convolution. When we have an infinite strip, this is the convolution with the hyperbolic cotangent. By periodization formula, when we are in the periodic domain, it gets worse. We have a Jacobi zeta function and elliptic functions to deal with, but our computations are made in the frequency domain. I'm currently trying to do some computations in the physical domain by means of the CD-Israeli alternate trapezoidal rule. And well, Janaína proved that there exists a unique local solution for this problem, in which this term is very important, because our lovely term here has not enough regularization. We have some difficulty with it. The spaces change a bit, but that's what we have for the moment. There are some, and we use parabolic regularization, the classical path for that. And we have also some conservation laws. In particular, this conservation law that generalizes the one Schombeck obtained, but it's essentially the same. She get to, here I have an error. This is beta divided by 3. The only difference with the Schombeck word is that we have this new term. This is very curious conservation law that it is obtained using lax pairs. Of course, when there is regularization, there is a decay, and we believe that that can help in the same way help Schoenberg to prove a global well-posedness in certain spaces. Maybe we can prove some global result for that system. This is our expectation. When the bottom is not flat, we can obtain a similar model which differs only in variable coefficient independent from time, and we do that by performing a conformal mapping in which our lower layer at rest, because of those asymptotic approximations, we can focus on this simplified situation up to the order of approximation we are considering. So we change to this computational domain, and the result, the result is this strongly nonlinear corrugated model for the lower order. For the higher order, I don't have a space enough to put here because there is a variable coefficient in front of each of the non-simple terms here. But just to show, for example, a weakly nonlinear corrugated model for higher order, you see again this same coefficient that came from the conformal mapping. And we can do things like study, for example, Bragg phenomenon for a slowly varying topography, and for rapidly varying topography, Daniel obtained an effective intermediate long wave equation. Here we have an average of that coefficient. If we have a slowly varying topography, we have an intermediate long wave equation. We always regularize with a variable coefficient. And I think that's it. So, thank you for your attention.